Okay. So again, the chemical equation is shorthand notation for chemical reaction. The reactants, the starting materials, are what undergo change. The products are what is produced. In an equation, the reactants are written on the left, and the products are listed on the right of the arrow. So we identify the products and reactants using chemical symbols. Like I said, reactants are on the left of the reaction arrow, products are on the right. Physical states of reactants and products may be shown in parentheses. What are those physical states? And you may see it in S, solid, L, liquid, G, gas, and AQ, which means aqueous, which means the substance is dissolved in water. If you have a triangle over the reaction arrow, it means that energy is necessary for the reaction to occur. So in our little reaction over here, obviously, if I want to make a cake, I got to put it in the oven. An equation must be balanced. An equation that's not balanced is useless. No, it doesn't. If I say, okay, I want you to make a cake, take some flour and some sugar and make a cake, odds are you're not going to be able to do a good job of it because you don't know how much of each. Plus, you don't know how much you're going to get. So here we have mercury oxide, solid. We're heating it to give us liquid mercury and gaseous oxygen. So the reactants are on the left, or in this case, reactant. It's a solid. We're heating it. We end up with a liquid and a gas. Hold on a second. Sure. Got it? Pardon? So a chemical equation represents a chemical change. One or more substances changed into new substances. End up with different chemical and physical properties. Obviously, if we go back to our example, flour and sugar have their own properties. And certainly a cake has its own properties. You don't sit down and eat, well, most of us don't sit down and eat a bowl of sugar or a bowl of flour. But, a couple pieces of cake, no problem. So again, one or more substances changed into new substances with different chemical and physical properties. Okay. How do you know a reaction occurs? If I just put A and B together, how do I know something happens? If I put salt in water, nothing happens. There's no chemical reaction. But if I put vinegar and baking soda, there's definitely a chemical reaction. What do you see? You ever put vinegar in baking soda? You see a lot of bubbles. That's the old make a volcano project when you were in grade school. So you can see a release of a gas. So CO2 is released when acid is placed in a solution containing carbonate ions. You can see a solid form, a precipitate. If I mix silver ions with chloride ions, I see a precipitate of silver chloride. Heat is produced or absorbed. Sorry, what?
Basically, when you see something happen.
Well, you don't necessarily see something happen. You could feel something happen. I mean, you're in the military, right? So MREs. Did you ever have an MRE? Meals ready to eat. Little packages, you add water to it, and it generates its own heat, cooks the food inside. So there, you're not necessarily seeing something happen, but you're going to feel heat. Or you see a color change. Or you see the emission of light. A glow stick. When you break the glow stick, there's a chemical reaction that causes the light, the compound to change, and it gives off light. So you can release energy. It doesn't always have to be heat. A lot of times it is. Or it could be the opposite. It could turn cold. So those are subtle indications. Heat or light is emitted. You can see that there might be a change in the way it behaves in an electrical or magnetic field before and after a reaction. They're changing its electrical properties. Certain patterns we can look at. There's a combination reaction. What do you think happens in a combination reaction? There we go. Exactly. Things combine. A and B goes to C. A decomposition reaction. What do you think happens there? Things come apart, decompose. Single replacement and double replacement. So a combination is the joining of two or more elements or compounds producing a product of different composition. A plus B goes to AB. So an example, sodium solid plus chlorine gas gives us sodium chloride solid.
That all would be the case with solid.
But a solid and a gas?
Solid.
Not always.
Most of the time.
Could form all gas. Could form, probably most of the time it's going to form a solid. But here we're talking about sodium, very reactive metal. Chlorine, and sodium is very reactive, hazardous. Chlorine is a very deadly gas. It'll kill you. Put them together, we end up with table salt. So the chemical and physical properties are completely different. And notice the formula tells you how they go together. I need 2 atoms of sodium with 1 molecule of chlorine. Remember, chlorine's diatomic. You get 2 molecules of sodium chloride. That's the way you have to put it together. So, a metal and a nonmetal to form a salt, which is just what we saw. Hydrogen and chlorine molecules to produce hydrogen chloride. That was actually one of your test questions. Formation of water from hydrogen and oxygen. So this is well, water in this case is probably a gas. Reaction of magnesium oxide and carbon dioxide to produce magnesium carbonate. So all of those are combination reactions. 2 things gives you 1. Decomposition, we start with one thing. Here we have AB. It goes apart to A and B. So the one we saw here was mercury oxide going to mercury and oxygen. Calcium carbonate, if you heat it, it's a solid. It goes to calcium oxide, a solid, plus carbon dioxide, a gas. Anybody know where you find calcium carbonate? Where? Yeah, Tums and Rolaids, calcium carbonate. It's also a form of limestone. Used to find it in schools in the old days. Chalk. So that's where people get their calcium from, you know, for osteoporosis and that. Ground up shells. Seashells. It's calcium carbonate. A removal of water from a hydrated material. So the copper sulfate pentahydrate, when we heat it and remove the water, that's a decomposition reaction. Single replacement. A plus BC goes to B plus AC. The A replaces the B. Example here, solid copper reacts with silver nitrate to give us solid silver and copper nitrate. Notice here, silver nitrate's in solution, aqueous. When we replace the silver with the copper nitrate goes into solution, and we're left with solid silver. Sodium plus water goes to sodium hydroxide plus hydrogen gas. And the bottom one, aluminum silver sulfide goes to silver and aluminum sulfide. That's the one I told you about at the beginning of the year, how you polish tarnished silver by putting it on aluminum. It's a single displacement reaction. Now I'm going to pause this. Okay, so we're continuing. So those are the type of single replacement. Double replacement. Oops, we missed that. Two compounds undergo a change of partners. So AB plus CD goes to AD plus CB. So they switch the front partners. An acid with a base, HCl with NaOH. The H goes with the OH to give us water. The Na goes with the Cl to give us salt. So that's a double replacement. PbNO3, the Pb goes with the Cl, so we get PbCl2. The Na goes with the NO3. So here we have, this is in solution, this is in solution. We do the reaction, we see a precipitate. In this case, it's bright yellow. And sodium nitrate stays in solution. So, how do you write a chemical reaction? Hydrogen reacts with oxygen to produce water. The first thing you have to remember is hydrogen is H2, oxygen is O2, and H2O. So you write it, and I put the numbers in there. Don't put the numbers in there just yet. It has to be balanced, and later on we're going to practice balancing equations. So a chemical equation shows the molar quantity of reactants needed to produce a particular molar quantity of products. What does that mean? If we go back to our bread example, the numbers, the 1, the 2, and the 1 are the molar quantities. Coefficients, those numbers in front are called coefficients. So I need 1 cup of sugar, 2 cups of flour, and I end up with 1 cake. Chemicals react in molar quantities, not gram quantities. So it's a whole number before each reactant. That's the coefficient. The law of conservation of mass says matter cannot be either gained or lost in the process of chemical reaction. So what you start with, you have to end up with. It's just a different arrangement. You can't create matter, and you can't lose anything. So here's a balanced equation for water. 2 molecules of hydrogen plus 1 molecule of oxygen gives us 2 molecules of water. If we look at molar masses, the molar mass of hydrogen is, molecular hydrogen is 2, because there's 2 H's, each one is 1. So you start with 4 grams of hydrogen, right? 2 moles, each mole is 2 grams. Oxygen, O2, has a molar mass of 32 grams, 16 times 2, 32, for a total of 36 grams. That's what we start with, mass-wise. We end up with 2 moles of water. Water is 18 grams per mole, 2 hydrogens, that's 2. Oxygen is 16, so that's 18. Times 2 is 36. So we start off with 36 grams of material. We end up with 36 grams of material. Law of conservation of mass. So the coefficients show how many moles of that substance have to be in the reaction, and it must be balanced. So all the atoms you start out with, you have to end up with. They just don't go away somewhere. So here we have 2 mercury on the left, 2 mercury on the right. 2 oxygen, the 2 multiplies everything in the compound. So 2 oxygen here. We have 2 oxygen here. So we got the same on both sides. So that's balanced. H2 plus O2 goes to H2O. Is the conservation of mass obeyed as is written? No. We have 2 hydrogen on the left, 2 hydrogen on the right. We have 2 oxygen on the left, but only 1 on the right. Yeah, so how do we balance it? We can only use coefficients. Here's a rule you remember. Never, ever, ever, never, under any circumstances, change the subscripts. If you change the subscripts, you're going to change the compound. You say, oh, we can balance it real easy. We just stick a 2 over here, H2O2. Well, then we don't have water. We have hydrogen peroxide. So it's not balanced. So that's wrong. Count the left. 2 hydrogen, 2 oxygen. The right, 2 hydrogen, 1 oxygen. Determine which elements are not balanced, do not have the same number. Oxygen isn't balanced. So we're going to change the coefficient, put the 2 in front of the H2O. So now we have 2 oxygens on both sides. But now the hydrogen's not balanced. Now we got 2 on the left, 4 on the right. So we have to put a 2 in front of the H2. Now we got 4 hydrogen on each side and 2 oxygen on both sides. So now it's balanced. So there's our recipe on how it has to go to. Notice we can't make 1 molecule of water. We have to make it 2 molecules at a time. Because we have to have 2 hydrogen molecules, 1 oxygen molecule gives us 2 water molecules. Pardon? Because of how hydrogen exists and how oxygen exists. Because they're both, you got to remember those 7. So again, here's balancing equation. Nitrogen plus hydrogen gives us, oh, N2H4, that's not right. Nitrogen plus H3, that's not right. N2 plus 3H2 gives us 2NH. That's the correct one. So balancing equations is a little bit of an art. So balance the following equations. First hint, If you have something with oxygen and hydrogen, do those last. Out of those two, the one that's by itself, do last of the last. So in equation number 1, you have carbon, hydrogen, and oxygen. We're going to do carbon first. So we got 2 on the left. How many we got on the right? 1. So what do I have to do? I have to put a 2 here. Next, we're going to do hydrogen, because that's not by itself. We have 2 hydrogen there. We have 2 on each side. Fine. Oxygen, we got 2 on the left. How many we got on the right? On the right. Nope. Nope. What did I say the coefficient does?
Oh, okay.
5 oxygen. Well, they started off with a hard one. So here we got 4 here and 1 here. So we have 5 oxygen. Okay? Everybody see 5 oxygen? Okay with that?
So it's 4 plus the 1.
Yeah. Yeah. So everybody's 5. We have a 2 on this side. So this used to drive me crazy. So I figured out the trick. What's 5 divided by 2? 2.5. 2.5. You can't have a 2.5. It's got to be a whole number. How do you make it a whole number? You can't round either. So you can't make it a 2 or a 3. What if I multiply it by 2, then what do I get? 5, right? That's a nice whole number. But if I multiply that by 2, I have to multiply everything in the equation by 2. So what's the coefficient here right now? You don't see one. What is it? 1. So 2 times 1 is 2. So now I have 2C2H2. 2 times 2.5 is 5O2. 2 times 2 is 4CO2. 2 times 1 is 2H2O. Now we check it. 4 carbon, 4 carbon. 4 hydrogen, 4 hydrogen. 10 oxygen. 4 times 2 is 8. 2 times 1 is 2. 8 and 2 is 10. 2 steps. Okay. The second one, silver nitride plus ferric chloride goes to FeNO3 3 plus AgL. Another hint, if you have polyatomic ions, try to balance them as a whole unit. So I have how many NO3s on this side? So I should need 3 on this. What do I need to put in front of this? 3. How many AGs? 3. So what do I got to put on the other side? 3. FEs, I got 1 on each side, right? How many chlorines? No. I have 3 on the right. 3 times 1 is 3. So we're done.
I mean, shoot, we probably already covered this, but how are we supposed to know if it's a polyatomic ion or something?
Okay. Well, here we see a metal, right? So that's a cation. Cation and anion should be, is this an element? How many elements do you see here? So it's more than 1, so it's polyatomic. We had that list of polyatomics, so you can kind of recognize them, especially if they're put in parentheses like that. So now you know it's a polyatomic. C2H6 plus, okay. Again, we're going to start with carbon, so I got 2 on the left, so I got to put a what? 2 on the right. 6. I got to put what in front of the hydrogen? 3. How many oxygen on the right?
Now you have 5.
Try again.
2 is 4 plus that 1. I mean plus that 3, so that's 7.
7.
I don't know why I always keep forgetting about your handwriting. I don't know what is it.
So I got 7 oxygen on the right. But I still have the O2. What is 7 divided by 2? How do I get rid of that? Multiply everything by 2. So it's 2C2H6 plus 7O2 goes to 4CO2 plus 6H2O. Then you check it. 4 carbons, 4 carbons, 12 hydrogen, 12 hydrogen, 14 oxygen, 8 and 6, 14. Bottom one. So I got to do the right. Put a 2. Now what do I need to do? Okay. There you go. Oh, this? This I'm only multiplying the coefficients, yes. Yes. All right, let's try some. Yeah. All right, see what you can get from this. Oh, by the way, you can see like copper's got a little silver tree on the bottom of it. Hmm? Oh, that's very delicate. That won't stay. So what's the first thing I'm going to do? No, what's the first thing I'm going to do? What am I going to do? You go to the H next. Put it right. How many oxygen I got on the right? How many oxygen I got on the right? No. No. 14 plus 8 is 22. 7 times 2 is 14. Oh, you can't forget about those. They're over there too. And 8 times 1 is 1, so I got 22 oxygen. So what do I put in front of there? 11. Oh, you just can't forget about those. Okay.
out loud until I said
Either way, somebody give me the first move.
so 3 in front of the carbon.
You put a 3 in front of the carbon? 6.
Yeah, you're right. It's only with oxygen.
Put a 6 here? You think? So now I got 12 hydrogen on each side. How many oxygen I got on the left?
13. Why am I forget that 6? It's the way you write them in. I'm telling you. It's because I'm not writing them myself, and I forget that you just wrote it down.
How many?
Yeah, right on.
18. 6 times 2 is 12. 6 times 1 is 6. 12 and 6 is 18. Okay. I really don't want to change this because I'd have to change everything else. So I could take these 6 oxygen, take them away from the 18. How many does that leave? 18 minus 6 is what? So can I put a number in there to give me 12? 6. There we go. Anybody know what that equation is? Besides hard. What? Photosynthesis. Carbon dioxide was water. Gives us glucose and oxygen. Okay. Again, it comes with practice. Let's see. Let's try this one. See if you can do that one. Oh.
It's 2 lines on the left, so there's 3 lines.
Done? You got it? There's nothing polyatomic there.
I think I understand the way you're writing.
Fe2O3 only has 2 atoms. Which one? When you have more than 2 either anions or cations. I would. You got it? No. No. So if I'm going to do the iron first, how am I going to do it?
It seems like it, how wrong is the one on the right just one more than the one on the left? So in this case, would you even bother with the coefficient?
You got to. I'm starting with 2 iron atoms and I'm ending up with 3 iron atoms. You can't do that. You can't create iron atoms. It's not balanced. I got a 2 on one side and a 3 on the other side. I got to look for what? Common denominator. What's the common denominator of 2 and 3? 6. So what am I going to put in front of the first Fe? So now the ions are balanced. What about the carbons? Are they balanced? Yes. There's one on each side. What about the oxygens? Are they balanced? Yeah, they're balanced. You got 9 here and 1 here is 10. 8 here and 2 here is 10. We're done. That was it.
Except that little trick that we didn't have any clue
Oh. Okay. Keep getting up the wrong thing. Here we go. Polyatomic. Done. We got it? Nope.
I deal with the polyatomic first since there's.
We don't have them on both sides, so you can't put.
I know, but.
So we got 2 CRs on both sides, right? That's fine. We got 2 nitrogens on both sides, right? Let's do hydrogen. We got how many on the left? 8. So what do I got to do from the H2O? Put a 4. So I got 7 oxygen on the left. How many do I got on the right? 7. 4 and 3 is 7. We're done.
What I was gonna say,
Yes.
I know that there's not a polyatomic on the right, so I
Okay.
wasn't gonna do the whole parentheses. I was just gonna say the same thing you said, because
Okay.
I was just dealing with every polyatomic on the left.
Yes.
And since I did that, I knew I ended up with 8 hydrogens, so I had to end up with 8 hydrogens on the right. Put a 4 in front, the oxygen is already done.
Yep.
Yeah, that's what I was saying.
Okay. You're right. Again, it comes from practice. So precipitation reactions, which is what you just see up here with the silver nitrate and the copper. It's chemical change in a solution that results in one or more insoluble products. So how do you know it's going to precipitate? We have to know about solubilities of ionic compounds. So here's its rule of solubilities. If the compound contains an alkali metal, anything in column 1, or the ammonium ion, the polyatomic ion, it's soluble. No exceptions. Nitrates, things that end with NO3, bicarbonates, HCO3, and chlorates are soluble. There's no exceptions. Halides, things that end with Cl, Br, I-, are soluble, some exceptions. Salts of silver, Hg2 and Pb2 plus are insoluble. Sulfates are soluble except for sulfates of silver, calcium, strontium, barium, mercury, and lead. This table is in your book. You don't need to copy it down. It's table 4.1. Insoluble compounds, carbonates and phosphates, are insoluble unless they have an alkali metal ion or the ammonium ion. So for example, sodium sulfide is soluble because sodium is in column 1. Barium sulfide is not. Hydroxides are insoluble unless they contain column 1 metal or the Ba2 plus. So sodium hydroxide, which is what I made over there in the beaker, is soluble. That's liquid Drano. Okay. Magnesium hydroxide, magnesium is in column 2, but it's not barium, is insoluble. So magnesium hydroxide, you find it in your grocery store if you have heartburn. It's milk of magnesia. If you've ever seen the bottle, it's a blue bottle usually, and it has a white liquid, opaque liquid that you can't see through. So that are little pieces of magnesium hydroxide in a suspension. Predicting whether precipitation will occur. Recombine the ionic compounds to have them exchange partners. Examine the new compounds formed and determine if any of them are insoluble according to the table. If they're insoluble, they will precipitate. So here we have lead nitrate and sodium chloride. Both of them are in solution. Double replacement. The lead goes with the chlorine. You got to know it goes to PbCl2. How do you know? What is the charge on lead here? Nitrate from the table, polyatomic ions, is -1. We have 2 of them, so it's -2. Compounds are neutral, so the lead has to be +2. Sodium, we know, is +1. Chlorine is -1. So if lead is 2+, we're going to combine it with chlorine. We've got to have 2 chlorines. Somebody's not happy about something. Here, sodium is +1, nitrate's -1. So then we look at our rules of solubility. Well, the sodium, column 1, we know it's going to be soluble. So that stays in solution. Here, this is soluble because it has a nitrate. All nitrates are soluble. Lead chloride, that's one of the exceptions for the halide rules. Halides are soluble except for silver salts and lead salts. So this is going to precipitate out. Potassium chloride and silver nitrate. Again, nitrates are always soluble. Column 1, potassium, always soluble. Goes to silver chloride. Again, we exchange the metals. and potassium nitrate. Nitrate, column 1, they're always soluble. Ag is the other exception for the halide, so we get a precipitate of silver chloride. So a chemical reaction occurs. Oh, let me see. So if we did potassium nitrate plus sodium chloride, plus potassium nitrate soluble. Yeah, because it's a column 1 metal, and all nitrates are soluble. So this is AQ. Sodium chloride soluble in water. I mean, you didn't have to go to the table for that. Yeah, salt dissolves in water. So if we change places with the metals, then we get sodium nitrate plus potassium chloride. Sodium nitrate soluble? Yeah. All column 1 metals are soluble and nitrates are soluble, so this stays in solution. Potassium chloride soluble? Yeah, because potassium's in column 1, and this is soluble too. So in other words, nothing happens. There's no chemical reaction. Okay? Got me? So just because you mix two things together doesn't mean something's going to happen.
Like metals, right? Like metals,
What about them?
they don't cause a reaction like together.
Not really that I can think of. So reactions with oxygen generally release energy. This is the combustion of natural gas. So obviously that's how you heat your house if you have a gas furnace. Rusting or corrosion of iron, we don't think of that, but this actually releases heat. Because it's such a large surface area, we don't feel the temperature coming out. Unless you go to Dick's Sporting Goods or Cabela's, and you get these one-time use hand warmers that have, you peel off the sticker and there's a little mesh thing underneath there. Those are usually fine ground particles of either iron or magnesium. So a lot of surface area, rusts really fast, generates heat. And that warms your hand, but it's a one-time use only. Oh, we're Wi-Fi connected. Okay. I don't know what that was just doing, but acid-base reactions, again, it's a double displacement. The hydrogen ion goes with the OH to give us water. The metal goes with the chlorine to give us a salt. So an acid and a base gives you a salt and water. Now, if you have an upset stomach, your stomach acid is hydrochloric acid. I wouldn't drink sodium hydroxide for that, but if you don't have Tums or Rolaids, you do have baking soda. Baking soda is sodium bicarbonate. That will neutralize stomach acid.
How about vinegar?
Vinegar is an acid. That'll make it worse. Well, let me put it this way. Well, actually, there is some evidence that vinegar can make it a little better because what it does is overstimulates the production of the mucus because you're adding acid, but I really wouldn't do that.
But it works. It works. I'm a living witness.
Okay.
It works.
Well, it can work. It has to stimulate one of your enzymes. But if you drink baking soda, a teaspoon, and a glass of water, it'll neutralize the acid. Of course, you'll burp like crazy because it releases CO2.
I mean, you don't think about this stuff. And the formula and stuff is pretty.
You don't think of what?
I said that's so cool because when you do everyday stuff, you don't think about
No,
the formula that comes with it.
that's right. So there is a method behind the madness, so to
Everybody
speak.
does chemistry every day.
That's right. That's why I try to get people to realize everything you do is chemistry. Yeah, you just learn the other language behind it.
Which is still English.
So when you bake, you're doing chemistry. Okay? Remember at the beginning of the year, the chocolate chip cookie recipe. It was chemistry. We just use different chemicals for it. So oxidation reduction reactions are the transfer of one or more electrons from one reactant to another. So here I had zinc, solid, copper sulfate. I put a solid piece of zinc into copper sulfate. I get solid copper, and zinc goes into solution. What I did here is a similar thing. I had copper, I put it into a silver nitrate, did the displacement, and you can see the fine needles of silver that have come out. I mean, that's how they plate chrome on the fixtures and that, or gold plating on the people who have cheap jewelry. Okay. It's a transfer of electrons. So, what do we call a transfer of electrons? Transfer of electrons, what do we call it? No, transfer of electrons.
Energy?
What kind?
I mean,
Transfer of electrons, it's in the name. We commonly know it as what? Go ahead. Electricity. Hey. Turns out most of the reactions in your body and metabolism are oxidation reduction reactions, so we're transferring electrons in our body. Okay. How do your computers work and your cell phones work? It's electricity, but batteries. So we're not hooked up to a wire anywhere, and we're transferring electrons. So essentially, we're just big batteries. That's all we are.
so when we sleep, we're dead batteries?
No, you're actually doing a lot when you sleep.
Oh, yeah.
Some of us do more than others. Some of them are doing that in the back of the class, but that's okay. Got that? Okay. All right. So, we'll talk about oxidation reduction later on. But calculations using the chemical equations, that's where this comes in. You need a balanced chemical equation. Right now, without a balanced chemical equation, it's worthless. The coefficients represent the number of moles of each substance in an equation. So let's go back to our baking recipe. How many cups of sugar do we need? 1. So think of the cup as the mole. We need 1 mole of sugar. How many moles of flour? 2. How many moles of cake do we get? 1. So if I want to make 2 cakes, how many cups of flour do I need? 4. Terrific. How'd you do that? By what? Oh, okay. If I need 6 cakes, How many cups of sugar do I need? No, 6. If you put 12 cups of sugar in that cake, that's going to be one sweet little cake. Because it's 1 to 1. I said, how many cups of sugar? Okay, I know. You heard flour, but I said sugar. Okay. Maybe that explains a lot of the grades. Okay, I say one thing, you hear something completely different. Okay. So you're doing it fine with the cakes, right? So if I'm making a recipe and I use 8 cups of flour, how many cups of sugar do I put into it? 4. Excuse me? What'd you say? 2-to-1 ratio. Yes, exactly. I wasn't questioning you. I just wanted you to say it so everybody could hear it. 2-to-1 ratio. So you have no problem with that. So you shouldn't have any problem when I take the flour out and the sugar out and put in ethane and oxygen and chemicals. Okay. So let's say I weigh the cup of sugar. And it weighs 200 grams. I weigh 1 cup of flour, and it weighs 100 grams. So I'm going to go make this cake. In my kitchen, I don't have any measuring cups. But I'm a chemist, so I have a scale. Can I still make the cake? How? Weigh it. Okay, so I'm going to make 1 cake. How much sugar do I have to weigh out? How much flour do I have to weigh out? 200 grams. 200. I need 2 cups of flour. Each cup weighs 100. I need 200 grams. Okay. I want to make 3 cakes. How much flour do I weigh out? 600 grams. See how easy that was? No problems? I know what you can envision, but you don't need to look at this, you don't need to look at this, and you don't need to look for this. I could put anything in there. I could put 1 rhinoceros plus 2 elephants. You know what you get when you cross an elephant and a rhinoceros, right? Elephino. Yeah, so you get 1 elephino. Okay, so it doesn't matter what you do. So we come over here, we can do all of this stuff on this side, right? And we could do all of this stuff on this side. To go from this to this, the flour to the cake, the sugar to the cake, we use the coefficients, the ratios, the numbers in the front. That's all we use. It's as simple as that. No, but don't get lost in the jargon. You can do it with cake and flour and sugar. Yes. Okay. Would you call me?
No.
I know. It's yeah. Okay.